here, and then that's right. So this function, they purposely made it look like it's going to be horrible and all that kind of crap, and it's not a big deal at all. Nothing is either case. It still looks like it's going to be weird. So how do you do the derivative? This.
So it's 101 x 100.
Yeah, this is nice and easy, right?
Plus 51 x plus 1 equalizes to 0.
Yeah, so you should already know what's going to happen if there are, where to say, prove that it has neither a local max nor a local min. The easiest way for that to happen is for there to be no places where that could happen. And where are the places where it could have a max or a min called? What are those called? Critical numbers. I love it. So the easiest way for a function to not have any max or min is for the function to not have any critical numbers. And how do you set this equal to 0? So if I want to set this equal to 0,
so
does anybody notice? Let me catch everybody. Does anybody notice what form this is in? This is the big thing here. Can you make this leap? So if I had instead 5x squared plus 6x minus 7 equals 0, how would you solve that? You start by trying to factor it. This won't factor, so then you use quadratic formula. I love it. That's quadratic, ain't it? Because that's half of this. That's all that's required for something to be quadratic. So then you'd say instead of x equals negative b plus or minus blah blah blah, you'd say x to the 50th equals negative b plus or minus blah blah blah. Why is there an x there? Because that's half of this. That's why it's in the middle. So what I'm going to do is 50. X to the 50 is going to equal that. And guess what this is going to be? This is going to probably be something. We'll see what happens. Complex, yeah. Is that cool? I mean, that's actually my guess and my memory, to be honest. I'm thinking that's probably what's going to happen. But all you have to do is check the what. Who remembers the name of it? What tells you it's going to be complex answers? The discriminant. I like it. I got to watch your faces, because now I realize when nobody's saying anything, some people are mouthing the answer. Like, give yourself some volume. So the discriminant is b squared minus 4ac. So check that out. See what happens there. All right. See, that's why that doesn't have any. I don't know. Yes.
69.
Yeah. Okay. Good. 69.
Can I also ask you, were we supposed to draw it? This one?
Oh, what did it say? No. Mm-mm. In fact, I'd rather you not.
No, I use decimals and it just looks like cube.
Yeah, exactly. You'd have to think, how could something not have a max or a min if it's defined everywhere? The simplest example of a function that does that is what? Cubic, x cubed. Because the only place that has a critical number, does the critical number actually indicate a turning point? No, it's just a temporary resting point, right? All right. Okay. 69. All right, how can I say this? There's kind of two levels to 69. First off, something that's a little bit evil is they want you to maximize the density. And to maximize density for a constant mass, oh shit. And you're all like, I didn't take chemistry, man. So many guys are like, I took too much chemistry. I know exactly what you're talking about. What is density?
Density, mass over volume.
Yeah, it's mass divided by volume. I like it. So if I have a volume equation, when is the density, and they're trying to find max density right here. When will the density be the biggest? When the volume is the smallest. I like it. So they give me an interval. They give me 0 degrees to 30 degrees. Celsius, the appropriate scale, right? Yes. So that's an interval they give me, and they ask me to find the maximum. So this is really what kind of a problem? Is it an absolute maximum problem, or is it a local maximum problem? They give me endpoints. It's absolute. They give me endpoints. I can find the critical numbers, and then I just have to plug all of them in there. They want the max density, which I know means they want the min volume. So you're going to do the volume at 0. Check that. You're going to do the volume at 30, and you're going to do the volume at whatever critical number you get when you take the derivative of the function they gave you. Does that make sense? I mean, that's the procedure for absolute maximum. Find all the critical numbers, and then check the critical numbers that are in here and the endpoints. See who wins. Yes, sir?
So, how do you figure out the critical numbers? Don't you take the derivative? It's like really small decimal.
Okay. Sorry, I got to be real mean for right now. I don't care what the numbers look like for us. I mean, we're in calculus. We're not scared by very small numbers, very big numbers. And you're going to set it equal to 0 anyway, and then you can make them as big or small as you want to, because you can multiply both sides by anything. All right, so you multiply a billion, make them stupid big, or not. Maybe just multiply it. So, you will end up at a place when you take a derivative of a cubic polynomial. Your answer is going to be what form? What will the derivative be in? Squared, quadratic. So then you can use quadratic formula. Is that cool? Yeah. I like it. Maybe. Okay, I can tell some of you guys are running scenarios in your head of what you would do to me if you could. But I'm just trying to help you through this. That's what I'm here for. Okay, anything else from homework?
What about 45?
45?
Tell me to graph it. And then calculate it.
Oh yeah, you definitely have to use...
It was weird though because I graphed it and it said there was 10 critical numbers, but I didn't
Definitely.
see how that, the graph that's like one.
So you ready? So two things might be happening. I don't know. Something might have gone into the graphic calculator incorrectly.
And that's supposed to be 10.
Did you put the... Oh, is that sine x? Where do you go? There it is. Oh, it's not sine x minus 1, it's sine x.
How do I do that? Just how do I type in sine x?
So when you type in, let's see. Can't remember now. I don't think it opens. Does it open a parenthesis for that? Sine, yeah, I think it does, doesn't it? So sine, see, that's really stupid. It's sort of like when you're working with Microsoft Word, and it says, did you mean this? No, Word. I know what I mean. Go away. I don't need your help. Did you mean to say this? Get away from me. I don't know if anybody else has that problem. So if you're trying to type in here, if you want to put in here sine of x minus 1, this is not right. Oh, you don't want to see it, do you? So when you hit the sine button, it opens a parenthesis. So if I want to put in there, if I want to put sine x minus 1, I have to close a parenthesis immediately. Right?
And 2 minus 1.
Yeah. So sine x, close it, minus 1. See, it always got to me about the older calculators. So they open the parenthesis for you, and you're like, that just messes me up. I know when I want a parenthesis. Stop putting it in there for me. Right? You know, little grumpy old man. Oh, stupid calculator. All right, cool. And then it should work out. The big thing with that problem, though, has anybody tried the problem out, number 45? They tell you this really ugly. And they say the f prime. Good. So I don't know if you guys remember, we've talked about this at least one time. What's the amplitude of this? Sine x, what's the amplitude? The amplitude is a thing that's sitting where? So sine x, what's the amplitude of sine x by itself? 1. If I wanted to make it 2, what would I do? Put a 2 in front of it. So the thing in front of the sine is the amplitude. Is the thing in front of the sine constant? No. In fact, the thing in front of the sine, as x gets bigger, it's getting smaller. So this is a damped wave. When you pluck a guitar string, thankfully it stops eventually, but theoretically it would go forever, just dampen down forever. Do you have to know all that to do this problem? No, but when you graph it, you know what to expect. But then it's shifted down by 1. At some point, sine is not going to reach 0. So let's come back. How do I find the critical numbers for anything? Take the derivative. They already did. So now I just have to look at, see where is this equal to 0. So how many critical numbers will this have? Is how many times does this hit 0? Right, they've already done the derivative for me, thankfully. I don't even want to think about what the original function looked like. Look at this. Shit. Yes? Okay, so graph this. It is the derivative. So where are the critical numbers? Where it's 0 or undefined, but in this case it won't be undefined. It's a nice sine function. Okay, so anything else from homework?
So we need just to graph it, but algebraically, can we do it?
Don't do this by hand. Whenever they have that little thing with a graph on it, they mean, dear God, use your graphing calculator, don't be insane. Right? So I would tell you directly on a test, if I want you to get your answer from the graphing calculator, I would be so explicit about that, because normally, you know me, I don't want you to do that. Yeah.
Could you possibly do it by hand? Is it possible?
It's not impossible, you just can't be, it might not be possible to be detailed enough. Yeah. Totally, yeah, it's doing your head, you're like, oh yeah, I got it, Jeff, I got it. Okay. Anything else from the homework? Okay, so we have section 4.2 to talk about. We haven't talked about 4.2 yet. And 4.2 is, I'm going to try something here. I'm going to show you this thing I keep talking about, the Desmos thing that somebody reminded me about. We're going to do some stuff in Desmos. Desmos. Aw, poor little dude. Okay. Yeah. Password is 1 2 3 4 5. All right. Oh, before we do that, let me get into this a little bit. So, let me ask you some questions that before we even talk about the idea. We talk about the actual procedure. If I have a function from A to B. And let me tell you something about the function. The function is continuous and differentiable. Continuous on AB, differentiable on AB. We're almost always a little more stringent on this, a little less stringent on that. See how it doesn't have to be differentiable at the endpoints, right? It's a normal thing we do. So here's like f of B. Here's f of A. Okay, so even before I draw the function, what is the slope between these 2 points? I mean, the function, what can the function be doing? All kinds of weird shit. But now I'm talking about as the crow flies. Right, from this point to that point. I'm not going to follow the path, because the path is crazy. I'm just going to go straight there. All right? What's the slope? Almost too easy of a question. Right? Maybe that's not why you're not saying anything. You're like, yeah, sure, Jeff. But what's the slope? What's the slope between 2 points? Good. Now, less wordy. More mathy.
F of B minus F of
Yeah, the difference in the y's. that rhymes with wise, which is almost too good to believe. Rise is the wise, run is the other guys. B minus A, right? So that's the slope of this as the crow flies, from that point to that point. Now, here's the idea. Whatever way I connect these, if I follow this, this means I can't jump around, right? It's continuous, so I can't just suddenly jump somewhere, and it's differentiable, so I can't have like infinite thing, and I can't have a cusp or anything weird like that. You guys kind of with me? All right. If you combine those two things, so let's say the slope is 2, for example, or whatever. If you go straight there, then the slope is always 2, right? If you just draw a straight line, the slope is always 2. That's amazing, Jeff. So what if I start drawing like this? At some point, will the slope have to be 2?
Yeah.
Think about it. Right now, the slope is
Some number.
bigger than 2, right? Isn't it? Because if it was 2, it would just go like that. So right now, that is slope. But to get there, it's got to it's got to have this, it's got to be parallel to that sometime. Does that make sense? You let that sink in for a second. So there's like 2 levels of this. You can get really lost in the details of trying to prove this, or you just step back and say, oh my God, of course there's going to be a place. It's got to be a place. If it starts going away from it, we're off course. Oh shit, we better correct. At some point we're going to be parallel to what we should have been doing, right? If I start going, oh shit, okay, at some point you're going to be, and maybe there'll be a lot of places where, right? So this theorem, the mean value theorem, says there's at least one place, take this weirdness out here, at least one place, we'll call it C, where f prime of C equals the as the crow flies. Alright, so let me give you a visual of this. I don't know why I asked permission, but I'm going to give you a visual. Stop. Alright. Oh. So there's my function I'm going to work with. You're just going to stay there, right? I'm going to work with this function x cubed minus x squared. Can somebody tell me something about x cubed minus x squared? Anything you want to say? What? Tell me something about it.
It's continuous.
Alright, it's continuous. I like it. It's polynomial, so we got that. Beautiful.
Factor.
You could factor it. So then from that you could find the...
Critical number.
No, you can't. Not by factoring that. I haven't done a derivative. But let's just stick with the function itself. If you did factor it, you could find its intercepts, right? It's x-intercepts, right? So if you factor this, you get that. What's the x-intercepts?
0 and 1.
0 and 1. I like it. Okay, cool. Right. So this actually ends up looking roughly like, here's 0, here's 1. It looks roughly like this. So we'll see that here in a minute. So my question is, on the interval from, what was your interval, Jeff? -1 to 1. What is that C value where it's got the same slope as if I went straight? So here's -1, and here's 1. Well, 1 will actually be 0. So if I went straight from there to there, is there somewhere in here where it's going to be parallel to that? It's got to be. It only makes sense that it must be. But now we're getting into the technical thing about how do I find that. So let's look at this. Let's visually look at it like that instead of auditorium. So here's what the function looks like, right? It's cubic, so we kind of expected this kind of thing. And as I'm doing this, you can see all the stuff you could do with Desmos here. It's kind of nifty. All right, let me stop there. Is that cool? So I did that just by typing that in. So if I click here, I can type in another function and put it on top of that, have it be a different color, so forth. All right, go away. I don't want you. I can do the derivative of the f, and I can graph it. So there's the derivative, exactly like we expected it to be. The derivative would be what? What's the derivative? 3x squared minus 2x. So it's going to be an upward parabola, and there it is. Right? So let me turn it off. I don't care about that. Go away. what I really want to show what's going on visually is I want to be able to see the tangent line everywhere. So watch this, watch this. Here's the line from, that includes -1 and 1. So that's what it looks like. If I do this line here. And how did I get that line? It's not nearly as hard as you think. How do I get the line between -1 and 1? Well, what's the slope going to be? What's f of -1? What's f of -1?
0.
-1 minus 1,
Oh,
-2. And what's f of 1?
1 minus 1. 0.
So what's the slope? -2 minus 0 over -1 minus 1.
1.
Slope is 1. Check. Now how do I get the actual function? Well, the way I do it is to just say y equals slope is 1, so 1x. And what do I do to 1 to make it 0? Subtract 1 from it. Alright, screw the mx plus by minus y1 shit, just make it work. Does it work for this? When I subtract 1 from -1, do I get -2? Yes. I have no idea if you guys understand what I just did, but you can just do the y minus y1 crap if you want to. I'm always trying to desperately show you don't have to do all that stuff anymore. That's algebra stuff. But you can if you want to. It still works. All right, so all I did was I got the tangent line, not the tangent line, I got the secant line between these two x values. So that's this line here. That's the as the crow flies. Are you guys cool with that? That's the as the crow flies. I just wanted to show you what it looks like drawn well for once instead of me, right? Okay, maybe. So visually what I'm trying to find then is the point C that's in here where the tangent line will end up being parallel to that black line. I like it. So what I did kind of in the background is I defined the slope. Now look at this right here. Look at this guy right here. What the hell's going on there? What the hell? I don't know. What's G? What's G? It's defined to be the what? Derivative. So that's the slope at C times x minus x1, x minus c, plus f of c. That was a lot like a linear approximation, but it's really just a tangent line equation. So why am I doing it based on c? Because then I can change what c is. So this is kind of cool. Watch. So if I do this, I can follow where c is. So right now c is -0.32, for example, so I can follow here. That doesn't show me much. But when I turn this guy on, bam, there's the tangent line everywhere. Let me see if I can... Oh, I forget how to change this guy's color. Oh well. But can you guys see that well enough? I don't know why it shows orange. Is that cool? Yeah, you guys can see that. I like it. So now, visually, can you guys see? As I'm dragging this along, alright, there's the slope, there's the tangent line in every... So there's like the 0, right? You zoom in a little bit. So we already knew that's a 0. And then here's another 0 place. Yahoo! So I'm looking for between -1 and 1, when is this tangent line parallel? So right there, now notice this. At 1 it actually is, isn't it? It's right on top of that bad boy. Do you guys see that? So at 1 it's parallel. Is there another place?
Right back. Minus 1, minus 2.
Right in here somewhere, right? Let's see, or maybe about right. Oh, Jeff, just give it up. Yeah, that's right. Yeah, screw it. All right, I kind of know the answer, right? So I'm trying. But that's almost parallel there, right? It looks pretty, to us, it looks pretty parallel. You guys understanding what's happening. So really all this theorem is, and once you realize what this theorem says, some people come to me and they say, well, what the hell's the use of that shit? But the mean, and this is true, you guys might not be there right now yet. Well, actually, you might just automatically say that about everything I tell you, but I understand. But this mean value theorem, the results are almost too obvious if you just think about it for a minute, that if it's continuous, there's got to be a place. If you don't go straight, you eventually have to go parallel to what straight would have been, or else how the hell would you get back here if you're like, no, I don't want to. No, I don't. Oh shit, you're never going to get there. Too bad for you. You got to turn and make it parallel to that. You got to. That's all this theorem says. But once we have it, it's used to prove so many other frickin' theorems in the future. Then you're like, you couldn't do shit if I didn't know this. It's like a building block is what it really is. So how do I find that point algebraically? Let's do that next. So that's the visual of what's going on behind the scenes. And by the way, if you want to use this website, they do have video tutorials, if I remember correctly. Somewhere you can click on,
Example.
probably this guy. Here.
That's cool.
And they have all these, there's derivatives, so forth. So you can click on those and they'll tell you exactly what to type in there to make certain things happen. So it's a really nice tool to use for the online. Okay, but how do I do this algebraically? I don't know. Let's see. What I do is I do exactly this, believe it or not. We have the algebraic stuff right there. So, let me take this away and put that back there. So what I want to do is I want to find a C, in this case, in -1 to 1, where the slope is equal to, keep walking people, what the slope would be straight from A to B. So as the crow flies, has to match the slope somewhere at least once, and there could be an infinite number of places. So this tells you exactly what to do. So what is f prime of C? What is f prime? You already said it, right? 3x squared minus 2x. So f prime of C is 3c squared minus 2c. And we already did that. The slope is right here. Is 1, right? Are you guys understand? So the slope between the endpoints, we did that right here. The slope between the endpoints is 1. Are you guys still with me? Or have you been with me at all? So I want to find a place on the function itself where the slope at that point would be the same as the slope between the endpoints. That's what this is doing. So this equals 1. So of course, hopefully everybody knows you subtract 1 so that you can factor this bad boy, and it is factorable. They won't always be, so you're going to use quadratic formula very often on these. How do you factor this?
3x.
So it's got to be 3c and c, 1 and 1. There's just no other way around it, right? You've got to love 3 and 1. You can only factor those one way. Now it's all about who's minus, who's plus.
3 plus.
To make -2, which one has to be negative? 3 or 1? 3. So where does that come from? So that's got to be negative. Because that's where -3c comes from. That's got to be plus. So then what are my two possibilities here?
1 minus
-1/3
and 1.
and 1. And 1 is not in here, is it? It's at an endpoint. So it's not even a valid thing to use. But -1/3, isn't that... Oh, too bad. What did we get there? We ended up at -0.34. And what's -1/3?
3.
-0.33333. Yes, maybe. Don't let that section, don't let it be too much. The algebra, the actual, not algebra, the computations are really nice. Now I'm not saying there are no weird conceptual questions in this section. There are. But they all relate to the idea that if I want to get from here to here, I have to eventually have my slope do a specific thing. So a lot of the conceptual questions deal with that. All right, so let's do one more. Let's do one more concrete example. So what if I said, let me give you one out of the book here. Blah, blah, blah. Sure. So use the mean value theorem to find the C that would make the slope what it's supposed to be. is this function one that the mean value theorem works on? What has to be true?
Yeah, be continuous.
Has to be continuous on the interval. Is that continuous on that interval? So when you see natural log, don't just automatically go, I can't do that.
Yeah.
Because it doesn't include where this thing is discontinuous. It's 1 to 4. Natural log's fine there. It's only not good at 0, right? And negative. Cool. I like it. So it's continuous. It's definitely differentiable because we know the derivative of it, right? I like it. Okay.